Marhaba. Okay, in this session we want to talk about a special kind of relations called equivalence relations, and they are very important in mathematics. Okay, so let's recall that we introduced what is a relation. A relation from a set A to B is a subset of the Cartesian product A cross B, and we studied several types of relations, namely reflexive, irreflexive, symmetric, antisymmetric, and transitive relations. Now I want to introduce what is an equivalence relation. So first we want to talk about relations on a set A. Okay, so let a relation R on a set A. So remember, a relation on A is a subset of A cross A, is called an equivalence relation if it satisfies three properties. It's called an equivalence relation if 1, R is reflexive, 2, R is symmetric, and 3, R is transitive. Let's quickly revise these three properties. Reflexive means every element in A is related to itself. Symmetric means whenever A is related to B, then B is also related to A. So whenever we have an arrow, we have a reverse arrow. And transitive means whenever a first element is related to a second, and the second element is related to the third, then the first is related to the third. This is called transitivity. So these three properties together turned out to make a very important relation, and we give it a special name, which is an equivalence relation. So we will spend this session studying equivalence relations. Now let's take an example on a set A. So let's take A. So here, this is an example. Let's take the set A, and which contains the integers from 0 up to 6. And let's define a relation on A. So let choose any two elements in A. So let M and N belong to A. Then we define M to be related to N by the relation R if and only if M is congruent to N mod 3. So this is how we define the relation R. So for example, we have that 3 or 2 and 5 are congruent, right? 2 is related to 5 since 2 is congruent to 5 mod 3. Because 3 divides the difference is negative 3, and 3 divides negative 3. Let's do the directed diagram. So so we have how many? We have 7 points in the set. And now let's name them. So here I have 0, 3, you'll see why, 6, 1, 4, 2, and 5. And now let's draw the arrows. So is 0 related to itself? Yes, because 0 is congruent to 0 mod 3 because 3 divides the difference. Is 3 related to itself? Yes, again, because 3 is congruent to itself mod 3 because the difference is 0. 3 divides 0. Similarly for 6. 6 is congruent to itself mod 3 because 3 divides the difference, which is 0. Okay, similarly, every element in the set A is related to itself by the relation R. So we have all these elements are related to themselves. Okay, so this means the relation is reflexive. Okay. Now second, is 0 and 3 related? Yes, because the difference is 3, and similarly 3 and 0 are related. So we have both directions here. And similarly for 0 and 6, right? Because 0 is congruent to 6 mod 3, and also 6 is congruent to 0 mod 3. So we have similarly for 3 and 6. Okay. Now 1 and 4 are related because 1 is congruent to 4 mod 3. And similarly for 4 and 1, 2 and 5 are also related, right? Because the difference between 5 and 2 is 3. And 3 divides 3. And here the difference between 1 and 4 is also 3. Okay, now is 6 and 4 related? No, because the difference is 2 and 3 doesn't divide 2. Now 6 and 1, the difference is 6 minus 1 is 5 and 3 doesn't divide 5. 6 and 2, the difference is 4. So these are the only relations we have. Okay, what do you notice now? That this relation, is it an equivalence relation? So let's check. So we've seen that every element is related to itself, so it is reflexive. Okay, so the relation is, this relation is reflexive, right? Because every element is related to itself. Second, it is symmetric because every arrow has a reverse arrow. Look, 6 is related to 3 and 3 is related to 6 and so on. So it is symmetric. And see, whenever 6 is related to 3 and 3 is related to 0, we find out that 6 is related to 0. And here as well, look, 4 is related to 4 and 4 is related to 1. So 4 is related to 1. You can check that it is also transitive. So it satisfies the 3 properties, and so this is an equivalence relation. Okay, now what do you notice about equivalence relations? We will see that this will be always the case. I'm talking about, you see that the elements of the set were collected in 3 different disconnected components. You see, we had 3. All of the elements 0, 3, 6 belong to the same component. 1 and 4 belong to the same component, and 2 and 5 belong to the same component. So usually we will see that this will be always the picture for equivalence relation. That once we have an equivalence relation, the elements will be collected together in separated, disconnected parts of the set. Okay, so subsets, right? 0, 3, 6 is a subset of A. Look, this is A. So here we have 3 parts, right? The first one is 0, 3, 6, and this is a subset of A, and this is the set 1, 4, and this is the set 2, 5. So notice that the union of these 3 sets is the whole of A, and these sets are completely disjoint, right? No element belongs to 2 different parts or sets. See, here we have 1, 4, and here we don't have any 1 nor a 4. Okay. Now these sets, subsets, motivates the following definition. So we can see A as follows. So this is A. It was partitioned into 3 subsets. Okay, the first set has 0, 3, and 6. The second has 1 and 4, and the third has 2 and 5. And what is the relation between elements in the same subset is that they are all related together by R. So here, if you want, this is the effect of an equivalence relation R on A. And what is the effect is that it divided the set A into three disjoint, pairwise disjoint parts. Okay, now how will we define formally what is this part? These parts are called equivalence classes. Okay, let me tell you what is an equivalence class, but before, let me tell you a terminology for equivalence relations, that if R is an equivalence relation, okay, on a set A, then when an element A is related to an element B by this equivalence relation, so no, it's an equivalence relation. When A is, okay, remember what does this mean? It means that the pair AB belongs to the set R. And what is R? R is a subset of A cross A. It's a set of pairs. Okay, if A is related to B by R, or if the pair AB belongs to R, what do we say? We say A is equivalent to B instead of related to B. So A is equivalent to B, and we write, so as a symbol, using symbols, A tilde B. So this means it is equivalent. Okay? Tilde is the symbol we will use for equivalent. And what does it mean that A is equivalent to B? It means that A is related to B by an equivalence relation, some equivalence relation. Okay, so this is a terminology, it's a language we will use here. Now, once we have an equivalence relation, okay, so from here, since 0 and 6 are related by the equivalence relation, we write 0 tilde 6. We also see that 2 is related to 5, or is equivalent to 5. 1 is equivalent to 4 via this relation R, which, how did we define it? That two elements are related if they are congruent modulo 3. Okay. Now these subsets are called equivalence classes, so let's define them. So suppose R is an equivalence relation on a set A, so say tilde is an equivalence relation on a set A, and choose any element X in A. We want to define what is the equivalence class of X. The equivalence class of X is the following set. Okay, before I define it, I will give the example that this subset, which contains, say, 6, okay, it contains 6, this will be the equivalence class of 6. It will also be the equivalence class of 3 or the equivalence class of 0. Okay, and this one is the equivalence class of 2. So how do you think, what should be the definition of an equivalence class? We denote it by square brackets X. So this is the equivalence class. This is the set of all elements in A. So all Y in A such that Y is related to X or is equivalent to X. So choose any element, collect all the elements in the set which are equivalent to it or which are related to it by the equivalence relation. This set will form the equivalence class of X. Okay, so in this example, we see that, okay, maybe I can make more space. Okay. here to write that the equivalence class of 6 in this example is all the elements which are related to 6, which are 0, 3, and 6. And the equivalence class of 3 is also equal to the same equivalence class as what? As 6, and also the equivalence class of 0 is all the elements related to 0, which are these 3 elements, 0, 3, and 6. Okay, why? Because 0 is related to 0, 3 is related to 6, 6 is related to 0 as well, and 3 is related to 0, because they are all congruent modulo 3. Now, what is the equivalence class of 1? It is all elements related to 1, which means all elements congruent to 1 modulo 3, and these are 1 and 4. And this is the same as the equivalence class of 4. And finally, the equivalence class of 2 is the set containing 2 and 5, and this will be the same as the equivalence class of 5, because all the elements which are congruent to 5 are 2 and 5. We are talking about this example. This is A, and this is the relation R, and it's an equivalence relation. Okay, now let's prove what we did, that the equivalence relation is the relation given in the example will be always an equivalence relation. Okay, let me state this in a more general form. So let M be any integer, positive integer. So above in the example we chose M to be 3, and let A be Z. So all integers. Above we only looked at the set A from 0 to 6. Now we want to look at the infinite set, which is the set of all positive integers, all integers. So 0 plus or minus 1 plus or minus 2 plus or minus 3, and so on. Now we will define a relation on A. Okay, so what is the relation? So let A and B be elements in Z, and we say A is related to B if and only if A is congruent to B mod M. Okay, in the same as we did in the example above, but M was 3. Now we want to show that this relation, defined in this way, is an equivalence relation. So this means we need to show it is reflexive, symmetric, and transitive. So 1, R is reflexive. Why R is reflexive? R is reflexive. How do you prove that a relation is reflexive? You need to show that every element in the set A is related to itself. So let A be an integer. A is the set of integers. Then A is related to itself because A is congruent to A mod M, since M divides A minus A, which is 0. Okay, so since A is congruent to itself mod M, then by definition of the relation we see that every element is related to itself. So it's a reflexive relation. Now second, R is symmetric. How do you show R is symmetric? Well, you need to choose any 2 integers in the set. So here we are dealing with the integers. Suppose A is related to B, then we need to show B is related to A. So what does it mean that A is related to B? It means that A is congruent to B mod M. And what it means that A is congruent to B mod M, it means that M divides the difference, A minus B. And what does it mean that M divides the difference? It means that A minus B is equal to Km for some integer K, by definition of divisibility. And what does it mean that, now multiply both sides by -1, then B minus A is equal to minus K times M. So b minus a is equal to an integer which is negative k times m. This means that m divides b minus a. And since m divides b minus a, this means that b is congruent to a mod m. And this means, by definition of the relation, that b is related to a. See what we did here? We proved that if a is related to b, then b must be related to a. This shows that the relation is symmetric. Okay, again, what are we doing here? We choose a positive integer m, we look at the set of integers, and we define a relation on A. So notice that here R is subset of Z cross Z. For example, so AB is an element in R, if and only if A is congruent to B mod M. Okay. We did the same above, but when M was 3. Okay, now it remains to show that that R is transitive. So 3, we will show that R is transitive. How do you show a relation is transitive? You choose any 3 arbitrary elements in the set. So let A, B, C belong to Z. Suppose A is related to B and B is related to C. So the first is related to the second and the second is related to the third. We will show that the first is related to the third, that is A is related to C, which means that A and C are congruent modulo M. So let's write now consider the following. A minus C is equal to A minus B plus B minus C. Do you agree? We just subtracted B and added B. Now, what do you know? Since A is related to B, okay, what does this mean? That A is congruent to B mod M. And this means that B is congruent to C mod M. Okay, this means that M divides the difference, and so A minus B is equal to Km. So A minus B is equal to Km for some integer K, plus here M divides B minus C. So this means that B minus C is equal to Lm. Now we can take M as a common factor, so K plus L times M. So this means that the difference A minus C is divisible by M. So therefore we prove that M divides A minus C, and this means that A is congruent to C mod M. Okay, so this means that M divides A minus C, which means that A is congruent to C mod M. Okay, and this means what? That A is related to C. Okay, and this is what we want. Look, we want to show transitivity, and transitivity means if A is related to B and B is related to C, we want to prove that A is related to C. Okay, so this shows that R is transitive. Okay, so moral of the story is that if we choose any positive integer M and we look at the set of all the integers and we define a relation on Z by saying an integer A is related to an integer B, if they are congruent modulo M, then we get a transitive relation. R will be, okay, so this is the conclusion, that this R is transitive. Okay, and by transitive we mean reflexive, symmetric, and transitive. So this is an equivalence relation. So let's take a particular example. So choose m to be 4. It's a positive integer. And now let's figure out, for example, what is the equivalence class. Okay, maybe, so imagine this is the set of all the integers. Okay, and let's choose 0. Okay, think of another integer which is related to 0. So 4 is related to 0 because 0 and 4 are congruent modulo m. 8 is -4, 12, 16, -8, and so on. So this is the first component of this relation. The second is 1, 5, 9, 13, and check all of these numbers are congruent modulo each other. Sorry, congruent modulo 4. You have also -3 and -7. For example, -7 and 5 are congruent. Why? Because what is the difference? They are congruent modulo 4 because -7 minus 5 is -12 and 4 divides -12. Okay, the third part will contain 2, and 2 is congruent to 6 and 10 and 14 and 18 and -2 and -6 and so on. All of these numbers are congruent modulo 4, and finally the last part will be 3, 7, 11, 15, -1, -5, -9, and so on. Okay, so check here, for example, 15 and 3 are congruent modulo 4 because, again, what is the difference? It's 12 and 4 divides 12. So what is this set? This is, for example, could be seen as the equivalence class of 4. These are all the elements related to 4. In other words, every element in this collection is congruent to 4 modulo 4. And this one is the equivalence class of 9, say. By the way, which is equal to the equivalence class of 1. And this is the equivalence class of 2, and this is the equivalence class of 3. Okay, this is also equivalence class of 0. So if you notice what's happening, that this relation, that A is congruent to B mod 4, divided the set of integers into 4 parts, 4 subsets, those which are divisible by 4. So these are, see, every element here is divisible by 4, or divisible by 4, or when you divide it by 4, you have the remainder of 1, or remainder of 2, or remainder of 3. Okay, so these are the four parts which the relation produced when it was applied to the set of integers. Okay, now in general, okay, I told you that it will always be the case like this, so we need to say a lemma here, okay, or if you want a theorem. So let R be an equivalence relation on A. Okay, and let AB be elements in A. So choose any 2 elements. Then the first observation is that the element A is an element of its equivalence class. Why is this? Again, what is the equivalence class? It's all elements y in A such that y is equivalent or related by R to A. But A is equivalent to A. Why? Because R is an equivalence relation, and by equivalence relation it means it is reflexive, and so A is related to itself, and so it belongs to the equivalence class of itself. Second, you need to see that if A is related, okay, I can write A is equivalent to B if and only if the equivalence class of A is equal to the equivalence class of B. So here I'm saying that look, 4 and 8 are related because they are congruent modulo 4, and you can check that the equivalence class of 4 is equal to the equivalence class of 8. Okay, and third, we see that if two equivalence classes are not equal. Again, so what is an equivalence class? It's a set of elements. It's a subset of A. What does it mean that two sets are not equal? It means that either they are disjoint or one element belongs to the first one, but it's not an element of the second one. Okay, two sets are not equal if they don't contain the same element. But in the case of relations, we have more than this. We have that they are disjoint. So two equivalence classes are not equal if and only if they don't have any element in common. It's not only that they don't have the same elements, they don't have any element in common. Okay, this is very important. That's why we have this partitioning. You see, this group, this collection of elements has nothing to do with this collection of elements. They are completely disjoint. There's no element which belongs to two different parts here. Okay, I'll prove with you. We proved the first one. Let's prove the second. So prove. So we want to show the forward direction. Suppose A is related to B. We want to show that the equivalence class of A is equal to the equivalence class of B. So these are sets. We show sets are equal by showing that one is subset of the other and the other is subset of the first. So let X be an element in the first one, in the equivalence class of A. Okay, this means that X, what does it mean that X is an element in the equivalence class of A? It means that it is equivalent to A. So X is equivalent to A, but we know, okay, since X is equivalent to A and we assumed that, and A is equivalent to B, then by transitivity, look, R is an equivalence relation, so it's transitive. So by transitivity, we have that X is related to B. And since X is related to B, this means that X belongs to the equivalence class of B. So what did we show here? That if you choose an element in the equivalence class of A, we showed that it's also an element in the equivalence class of B. So therefore, or thus, we proved that the equivalence class of A is a subset of the equivalence class of B. Okay, similarly, you show the reverse, the converse, which means that the equivalence class of B is a subset in the equivalence class of A, and so since two sets are subsets of each other, they are equal. So what is this? This is all the elements related to A or equivalent to A, and this is all the elements related to B. So we proved that if two elements are related, then their equivalence classes are equal, which means if two elements are related, then they are related or equivalent to the same elements, to precisely the same elements. Okay, so we proved this direction. Now we want to prove the reverse direction. If two elements have the same equivalence class, then they must be related. Okay, let's prove this. So this is the reverse direction. Suppose A and B are elements in A and they have the same equivalence class. Now by part 1, we know that A belongs to the equivalence class of itself because the relation is reflexive, but from our assumption, the equivalence class of A is equal to the equivalence class of B. So A belongs to the equivalence class of B because A is in the equivalence class of A and the equivalence class of A is equal to the equivalence class of B. But this means, by definition of the equivalence class of B, that A is equivalent or related to B. Okay, and this is what we want to show. See? We proved that if they have the same equivalence class, then they must be related. A is related to B. Okay, I'll leave number 3 for you as an exercise, that if two equivalence classes are not equal, then they must be disjoint. Not only not equal, disjoint is stronger than not equal. They are not equal and they have nothing in common. Okay, notice that 2 and 3 together gives us 4, which says that if A is not related to B, so if A is not related to B, then the equivalence classes are not equal, and if they are not equal, they are disjoint. Okay, so this means if you choose any two elements and you find out that they are not related, then their equivalence classes have nothing in common. Okay, so for example, here look at 9 and 6. 9 is not related to 6 because 9 is not congruent to 6 mod 4. Because the difference is 3 and 4 doesn't divide 3. And look here is 6 and here is 9, and these elements are, this is the equivalence class of 9 and this set is the equivalence class of 6, and you see you don't have any element in common. There is no integer which is congruent to 9 mod 4 and also congruent to 6 mod 4, which means no element, no integer which is related to 9 and 6 mod 4. Okay, let me finish this session by the following observation. So look what happened to Z here. It was divided, partitioned into subsets of Z, and these subsets are disjoint, pairwise disjoint. So this picture motivates the following definition, which is called a partition of a set. Okay, so let me write it. Suppose A is a set, so we are given a set. Then we say a partition P of the set A is the following. What is a partition? Okay, it's a collection of sets, is a collection, okay, P's, let's call it, of sets. Let's call the sets A1, A2, up to AN, such that, what do you know about these sets? First, each AI here is not empty. So every set here contains some element, and each AI is a subset of A. Okay, so these are non-empty subsets of A, of a set A. Second, if I is not equal to J, so if you choose different sets from these, then they are completely disjoint. Then AI intersection AJ is empty. So if you choose different elements from the partition, they don't have any elements in common. And third, if the set A is the union of all of them, so A1 union A2, union and so on A3. So this means that every element in A is either in A1 or in A2 or in A3 and so on, or in AN. Okay, so what is the picture of all? What is a partition? We have the set A, we have non-empty subsets of A, and they are disjoint, they don't have anything in common, and they cover the whole set, which means their union is the whole set. So this is A1, this is A2, this is A3, this is A4, A5, A6, A7. So this is a partition of the set A. It's a collection of non-empty subsets of A which are pairwise disjoint, and their union is the whole of the set A. Now, okay, we've seen this before. We've seen that that when we have an equivalence relation, for example, we can partition the set. Remember, we had 0, 3, 6, 1 and 4, and 2 and 5, the very first example, right? This was A, and we worked that A is congruent to B mod 3. Or the example about the integer mod 4, we also divided the set of integers into 4 groups. Remainder 0 after division by 4, remainder 1, remainder 2, remainder 3. So I hope you can see that partitioning a set and having an equivalence relation are two faces of the same coin. Okay, so let me elaborate on this. Suppose R, suppose R is an equivalence relation on A, then I will tell you what is a partition on A. So the partition PR will be the set. What are A1, A2? Here they are the equivalence classes of every element in A. Okay, so this is a partition of A. Okay, so for example, here the first set, this subset, this is A1, and this is A2, and this is A3. And what is A1? It's, you can choose any one of these, and this will be the equivalence class of 0. A2 is the equivalence class of 1, and A3 is the equivalence class of 2. So if you put them in a set, this will be the partition defined, induced by the equivalence relation R on the set A. And here, what is the set? Here A is the integers from 0 up to 6. Okay, so this is A. So this shows that if you have an equivalence relation, we have a partition of the set A. Okay, why it's a partition? You need to see that equivalence classes are disjoint. And why they are disjoint? Because of this, because of number 4 here. See, if two elements are not related, then their equivalence classes are disjoint. And by number 1, we know that every element belongs to the equivalence class of itself. So this means that the union is the whole set A. Okay, so again, let me say that these 4 points shows that an equivalence relation induces a partition of the set A. And what is a partition? It's a collection of non-empty pairwise disjoint subsets of A whose union is A. Okay, so you need to see why. You need to see why this is a partition, because of what we proved above. Now, on the other hand, suppose we have a partition. So suppose P is a partition of some set A, A1, A2, up to AN, is a partition Okay, suppose it's a partition of a set A. Okay, then what do you know? That these are non-empty subsets, their union is A, and they are pairwise disjoint. Then we can define an equivalence relation. Okay, let A, B belong to A. Choose any elements, then we define A to be related to B if and only if there exists some subset AI such that A belongs to AI and B also belongs to AI. So this is how, again, what we are doing in this part. We have A and we are given a partition of A. Then from this partition, we will define an equivalence relation by saying A is related to B if they belong to the same partition. So here is, say, A1. Now here you have C and D are related, E and F are related. Okay, X is not related to Z, but W is. X is related to G because X and G are in the same part, and U and V are related because they lie in the same part. So here you can see that A is related to B, U is related to V, but A is not related to Z because here is A and here is Z. They don't lie or they don't belong to the same part. Okay, so just to make this clear, what I'm saying that if you have an equivalence relation, then the equivalence classes of the equivalence relation will form a partition of the set A on which we are defining the relation. And on the other side, if you have a partition, then it will look like this. We will partition the set A into non-empty subsets, and now we obtain a relation defined in this way. Two elements are related if they belong to the same part. We call A1, A2 parts here. These are called parts. Okay, so once we define this relation, the claim is that this relation is an equivalence relation. So R, you need to see that R is an equivalence relation. And what does this mean? That it is reflexive, symmetric, and transitive. Why it is reflexive? Because A is related to A because A belongs to the same part as itself. And if A belongs to the same part as B, then B belongs to the same part as A, so it's symmetric. And if A belongs to the same part as B and B belongs to the same part as C, then A belongs to the same part as C, which means it's transitive. So all what I'm trying to show is that equivalence relations and partitions are two faces of the same coin. Okay. So this is what is a partition of a set A.